to introduce our next speaker, Abhinav Anand. Abhinav Anand is an incoming postdoctoral fellow at the Department of Electrical and Computer Engineering at Duke University. He did his PhD in the Department of Chemistry at the University of Toronto under the supervision of Professor Alan Ashbru-Guzik. His research primarily focused designing algorithms that use near-term quantum devices to solve problems in chemistry, physics, and machine learning. And with that, I'm going to pass it on to Abhinav.
Oh, great. Thank you for the introduction, and thank you for giving me the opportunity to speak at this conference. I'm sorry that I'm not there in person. I would have loved to be there in person, but I could not. Okay, let me start with my talk. So today I'll try to give you a brief overview of variational algorithms, and I hope by the end of this talk, you will have some understanding of why people are interested in variational algorithms and what are some of the challenges and some applications that people have thought about. Okay, so to begin, so to motivate why people even thought of variational algorithms, I'd like to start with this timeline where when the first use of quantum computers were proposed in I think 3 decades ago now. So early 1980s, when people like Yuri Amanin, Paul Benioff, and Richard Feynman proposed the first quantum computers, or proposed basically the use of quantum computers for simulating physical processes. It took a while for the first universal quantum computer proposal, but that was also proposed in sometime in the 80s. But the next, the first wave of interest in quantum computer actually started in the 90s and continued until late 2010s, where basically several key algorithmic developments were proposed, factoring, phase estimation, amplitude amplification, Hamiltonian simulation, amongst others. And also the proposal of quantum error correction codes, which you just heard about, was also first introduced in the 90s. Obviously, a lot of experimental progress was also made, like the first experimental demonstrations of qubits and different systems was also seen in the 90s. And in the 2000s, there was a slow and steady progress, but people realized how hard it is actually to build a quantum computer. So the experimental side had a lot of steady progress, but it was the software or the research theoretical side which made a lot of progress during this. And actually, what happened was in 2015 or after mid-2015, the first quantum computers were online, like a few qubit devices from IBM, Rigetti, and others went online, and people had the opportunity to actually run stuff on quantum computers, right? So we had these quantum computers available to us, and people were thinking, okay, we know that these devices are very noisy. They have a very limited connectivity. They have limited coherence time. What can we do with that, right? That was the question that people started to ask. And I think during that era, a lot of people thought about it, and this led to the proposal of what we call the variational quantum algorithms. And since then, there have been algorithms proposed for almost every aspect of physics or everything that we want to do with quantum computers. There is a variational algorithm for that. So that's kind of like where we are right now. And to shift the whole timeline and show it in terms of the number of qubits and the error rates of the existing device, I like to show this picture, which is taken from a talk that John Fresco gave. And this picture is still very relevant. It's 5 years old now, or almost 5 years old now. But 5 years ago, John Fresco gave this talk, and he told us that we are in this era called the NISQ era, where we have devices that might have like hundreds of qubits, but the error is that they would have like a very significant error. and it probably will take another, I don't know, 5 to 10 more years before we can actually start doing fault-tolerant quantum computation on single qubits at least. Or it might take decades. No one knows. But we will have these devices which are noisy. So what can we do with it, right? So there are different application areas that have been proposed. And so this is where the whole variational quantum algorithm picture comes in. So what is a variational quantum algorithm, right? So let me give you a very big picture overview of variational quantum algorithm first, and then I'll dive into the details later. So when I say variational quantum algorithm, what I mean is like it has these blocks that one can build, and once you make these modules and put them together, then it becomes a full kind of like an algorithm. So one of the first block is this thing called objective function or cost function. Oh. Sorry. Okay. Was there a question or no? Okay. Anyways, so let me move forward. So this thing called objective function is basically the thing that you want to solve, right? So let's say you want to find the ground state energy, or like solve a state preparation problem. So you can define this objective function, which basically encodes the problem in terms of minimization problem. And this can be done because the variational principle, based on the variational principle, which hopefully everyone is familiar with, which tells us that if you have a Hamiltonian, if you encode the problem into the Hamiltonian, you can basically find, if you can find the minimum state, it's going to be lower bounded by the exact ground state energy. So it basically, the goal becomes is to find the most like the lowest energy possible and turn it into a minimization problem. So once you have defined the objective function, the next thing that you do is you kind of like use the quantum computer to prepare certain states that correspond to the solution to your problem. And so basically that is what we use the quantum computer for preparing states, or we call it trial states or ansatze, which is just a guess wavefun or guess states for your problem. So you basically use the quantum computer to prepare these states, and I'll dive into the details of these circuits later. And then basically what you do is you read out or you measure the state corresponding to your objective function. You feed those measurements to a classical computer, which basically calculates this objective function based on the measurements and the parameters that you gave that you had in the device. And the classical computer basically tells you, okay, the next set of parameters, it gives you the next set of parameters corresponding to which you prepare another state and you measure, and the classical computer keeps on doing this kind of like iterative procedure until the state that you have prepared on the quantum computer is a very good approximation to the solution, or it is close to the solution that you're after. So this kind of like approach is using kind of like the best of both worlds. So like using classical computers to do arithmetics and calculate gradients and stuff like that, which they are pretty good at, and using the quantum computer to prepare quantum states, like prepare states basically, so which they are good at. So it is this hybrid approach that makes this and this modular approach that makes variational algorithms really interesting. And one can basically like once you know what problem you want to solve it, you can just encode it into this framework and have a variational algorithm. So let's dive into some details about. Let me begin with the objective function. So the first thing that you do in an objective function is to encode the problem. And usually you encode the problem by defining a Hamiltonian. And this Hamiltonian can be written as this sum of polywords or poly terms which is basically pKs here. So you have you can, and I'll show an example in the next slide. But it's basically a sum of a linear combination of different poly strings, and a poly string is nothing but a tensor product of these polymatrices, these four polymatrices that I have included the identity as the fourth one. So you can basically, if you can encode your problem in the Hamiltonian and write the Hamiltonian, then you can write your objective function using some function of, let's say, your Hamiltonian, the circuit that I showed, and basically this becomes your objective function. So the goal would be to find the optimal parameters which basically correspond to the ground state or to the solution of your problem. And this is what you basically, so what I've shown here is just basically an expectation value that you need to calculate, and calculate the objective function iteratively until you reach the optimal. So let's look at a simple example, right? So let's say if we wanted to have an algorithm that prepared the state, a single state in the state zero, right? Because we don't know if that was. So a simple way to write the Hamiltonian here would be just a projector onto the state zero, which can be expressed in terms of these poly terms. And then one can basically use this Hamiltonian to write the objective function. The objective function is nothing but calculating the fidelity of the guess state with the zero state here. And so that is what becomes your objective function here. So you can very easily define your objective function given the problem that you are after by just defining, by encoding your problem in the Hamiltonian. So that's the objective function. So the next thing that we want to look at is, okay, how can we prepare these, how can we prepare like the guess state on the quantum computer, right? So like the quantum circuit. So usually you would see pictures like this, where what you want to do is you want to prepare some guess states, and these gates there are some common gates that I've shown here, which people use to construct these circuits. So you can like there are different ways to construct these circuit, but they can be broadly categorized into two ways. One is called this problem inspired ansatz, which is a type of circuit that you construct based on the problem at hand. So let's say you wanted to solve that. So the thing that I've shown here is this is a unitary coupled cluster ansatz, which is a very popular ansatz for chemistry, which comes from like solving electronic structure problem, or solving the spectrum of or finding the spectrum of a molecule in chemistry, right? So you can use these information already that you know, given the configuration of the molecule, you can construct this circuit based on the configuration of the molecule. But the problem with these type of ansatz is that they are usually very long. And given, as I was saying, that the current quantum computers that we have are not they don't have that high coherence time. So like they're very noisy. So you probably could not run something like this for any significant problem. So an alternative to this is what is known as this hardware efficient ansatz, where what you try to do is you try to build short circuits which are expressible. By that, what I mean is like you kind of like try to build short circuit that can approximate the solutions that you're after. But there's no such like rule to constructing hardware efficient these kind of circuits. People usually just construct layers of these circuits and repetitively kind of like repeat it a few times in the hope, again, as I said, it's more like wishful thinking that, okay, if I repeat it more times, I would be able to reach the solution that I'm after. But then again, there's some problems associated with these circuits. Is like if you have no idea of like how to build these circuits, you might end up in this problem. So like you might not be able to optimize these circuit towards the solution. Like problems like parent plateaus and stuff are there. but you can run them, or there are different research areas where people are trying to understand ways to actually build this more efficiently. Okay, so that's the circuit part. Then the next part is basically how do we measure stuff, right? So one of the things that you can do very easily on a quantum computer is measure like the expectation value of in the sigma z basis, which is basically the computational basis, right? So if you prepare a state psi, which again I'm just using an example, 1-qubit example here, which is just a superposition of 0 and 1. Then if you basically want to measure the expectation value of C, what you do is you measure the state, and what you want to do is you want to estimate alpha or beta, so to say. And alpha can be done by repeating like the measurement. So like you have to repeat the measurement, like let's say some number of times, and given the number of times that you got alpha, or like 0 or 1, you approximate alpha and beta by that number. And once you have that, you can just write the expectation value of sigma c very easily. And then similarly, you can also write the expectation value of the other Pauli operator, sigma x and sigma by just adding simple gates to your circuit that was preparing the trial state. It's just a simple unitary transformation that you have to do. So like once you can measure like as I said, like your Hamiltonian can be written in terms of these Pauli bases. So if you're able to measure your trial state and any of these bases, then you should be able to kind of like estimate any expectation value, right? Is there a question, or am I just hearing something? No, okay. No, sorry. Yeah. So this is how you are able to like calculate the objective function and then iteratively kind of like optimize it by just measuring in the standard basis and like kind of chopping and changing like the circuit to make sure that you're able to measure any observable that you're after. And the final part of the variation algorithm is like optimization. So like the classical computer trying to calculate or trying to find the next set of parameters to tell. And the most common approach are gradient-based methods, where basically what you do is you try to like calculate the gradient, and there is like a really nice result in the field where you can just do like two runs of the same circuit and find these gradients very easily by doing the same expectation value measurements that you were doing. There are other gradients as well. Like people have also looked at natural gradients, where instead of just looking at like the normal gradient, you use the information about like the surface geometry and stuff, which can give you like faster convergence and stuff like that. But I'm not going to go into details of these. And there are other kind of like approaches as well, like gradient-free methods, something like evolutionary strategies, reinforcement learning, and things. So yeah, like one can do this very easily on the classical computer, the way you do it for any like normal classical algorithm. So this was just a brief overview of like what variational quantum algorithms are. And I now wanted to give you like some of the applications without going into the details of each of the applications. So as I said, like the first proposed application was for calculating or approximating ground state energies of molecules, and this was proposed in like 2014. And this is called the VQE, where what you do is you write the molecular Hamiltonian. And the objective function there is to just basically minimize the energy of your guess function, and then you keep on minimizing until you you basically repeat until you reach the ground state approximation of your molecule. So this was one of the first proposals. Another one was this called QAOA, which is basically trying to solving some kind of like optimization problem on a quantum computer. So something like maxcut or things like that. And it has been like modified. These two have been modified over the years to do so many like for different applications. Another area is this thing called quantum autoencoders. This is basically to find like efficient representation of quantum states. So given we are in this era where we only will have a few qubits, the proposal of quantum autoencoder was basically to try to reduce the cost of storing or cost of representing a quantum state on a quantum computer. And finally, there's a lot of stuff in machine learning or generative modeling, where there have been a lot of proposals for quantum generative adversarial networks to kind of like do generative modeling in ways like you can like the machine learning thing. So again, there's just too many of them, and I don't think I can go into all of them, but like just to give these are probably one of the more important like applications of the variation algorithms right now. But again, as I said, things are not like until now. It feels like, oh, everything is so working. So why are we not able to run these things successfully or demonstrate this quantum advantage that everyone talks about, right? So there are a lot of problems, right? And the biggest problem is noise, right? So in principle, like the whole algorithm looks okay. It's kind of like, yeah, it should work, and in principle, right? But because the circuits that you're trying to implement, and I think they are not exactly what you want on the quantum computer, right? Because noise is there. So we have to consider that in our variational algorithm without having to go, like, we know that we don't have the ability to do quantum error correction now. So we need to think about how we can reduce the effect of noise, at least in the next like few years, while we have these small devices before quantum error correction comes into picture. And then the other thing is resource, right? Like we only have a few qubits left to us. So and they have limited coherence time. So we need to figure out ways to kind of like use these resources very efficiently. So like something like an autoencoder, which reduces which tries to find the most efficient representation of quantum states. There needs to be like more efficient use of the quantum resources. And one of the main problems with that is we don't have kind of like a set way of designing these circuits right now, or how to use these. So people are like most of the algorithms that are in use today, they use the circuits that are in use are very frugal, so to say. They're not the most efficient circuits that one can use. So there probably needs to be a lot of work in that direction. And finally, we need to reduce the cost of optimization. Okay. I was hearing some feedback. No, okay, sorry. Yeah, so like we still need to reduce the cost of measurement. As I told you, that to estimate these expectation value, you have to run the quantum circuit thousands and thousands of times just to do one objective value or one expectation value calculation. And in large problem, this number can grow quite significantly. And if you want to do optimization, which is like iterative procedure, you'll have to run that like even more number of times for every parameter. So as the number of parameters in your circuit increase, the cost of optimization kind of like starts going like high. So there needs to be ways to reduce this whole cost. So these are some of the problems that kind of like are some of the more important problems that we have to solve before we can actually run some important problems using variational cognitive. So where are we right now? So again, as I said, we are still here in this NISC era. Maybe we have moved a little bit to the right, but we need to keep working on maybe better applications. Right now, we are very focused on as I said, chemistry and machine learning, but maybe there are other applications that might be useful or that one can use the quantum computers to solve. As I said, noise is a big problem, and we cannot do anything until we address that. Given we will not have the ability to do error correction in the near future, or so probably better error mitigation protocols. And finally, we do need better algorithms that kind of reduce the use or the wasteful use of quantum resources, or reduce the number of resource requirement for doing these things. And finally, I wanted to leave these for resources which are for different reviews that might be useful to everyone to get the stage where the field is. With that, I'd like to thank you and would be happy to answer any questions.